Okay, welcome back everyone. In this video, we're going to talk about the RL circuit. So what is it? How do we analyze it? And what kind of effects are there on current and voltage in this type of circuit? So first of all, we'll start with the definition. It's a circuit that has a resistor and an inductor. So that's why it's RL. Earlier in the course, we studied an RC, which was resistor and capacitor. And the RL circuit is going to be very similar to the RC circuit mathematically. So if you're able to follow that math, this shouldn't be too bad. But the idea is that the inductor is going to be opposing the change in the current through the circuit through its self-inductance. So let's take a look at a picture of an RL circuit with the switch closed. So when we close the switch here, we're going to have an EMF in the battery, and then we're also going to have a back EMF, which is this EL in the inductor, and we're also going to have a voltage drop in the resistor. So using Kirchhoff's laws, the total voltage drops and gains in a total loop is going to be equal to 0. So we have E for the battery minus IR for the resistor, so that's VR right there. And then EL, as we discussed in the last slide or presentation, is going to be L di dt. And that's going to be equal to 0. The sum of the voltage drops and gains in a closed loop is equal to 0, Kirchhoff's law. So when we did an RC circuit, this was a little bit different because we had dq dt for current, and then we had q over c, or q over v, sorry, for the capacitor. So analyzing this is not going to be any different, but we're going to get the current as a function of time instead of the charge as a function of time. So first thing I'm going to do is divide everything by L and bring di dt to the other side. And then I can pretty much instantly integrate this, and this would go from, whoops, we have a couple more things to do, my bad. Then we want to rearrange this and separate variables, okay? So we would have, for example, dt over L is equal to di over E minus IR. And we would integrate that from 0 to t and make it t prime to make math people happy. And then the current would actually go from 0 to a later value I. So that's di prime and I prime. Okay, so the dt prime over L will just integrate out to give us t over L. And di over E minus IR is going to be the natural log of E minus IR. But we're going to need to put a constant in there to make sure that when we then take the derivative of this, that we get just E minus IR. So we have to multiply by -1 over R. And we will evaluate this going from 0 to I. So we're going to bring the -1 over R to the other side, and we're going to get negative R over L times T is equal to the natural log of E minus IR all over E. And that's plugging in I and 0 for I prime. So then the next step would be to exponentiate this. So this is where exponential decay comes from that we talked about last time. So I'll just write it like this: E minus IR all over E is equal to exponential to the minus R over L times T. And we can simplify this and write this as E minus E to the minus R over L times T is equal to IR over, oops, sorry, that's correct, just IR. And then we can solve this for I by dividing by R. So we can get that I is equal to E over R, which you might recognize as I max, times the value 1 minus E to the minus T over L over R. Now the reason I wrote it like that is because L over R is also known as tau RL, which is what we call the inductive time constant. So more on that in a moment. But let's think about this. Does this make sense for our description of what we said would happen? We said that we had current in time, and at t equals 0 the switch is turned on, and instead of jumping up immediately to I max, the current gradually increases because of the back EMF from the inductor. So that makes sense, and this is our equation for closing the switch. Okay, so when the switch is closed, this is what's going to happen. All right, so now let's look at what happens when we open the switch, and in this case, we're going to have an EMF that is going to, whoops, went too far. When the switch is open, we're going to have an EMF that's actually going to help us because we no longer have an EMF from the battery. Okay, so basically what we'll have is VL or EL plus VR is equal to 0. So we have EL in the inductor and we have VR in the capacitor. Okay, so L di dt plus IR, remember these are both negative but that cancels out, is equal to 0. And we can write this as L di dt is equal to negative IR, and then we can quickly write this as negative L over R. Whoops, let's write this a little bit different. Let's write it like this. Let's say di over IR is equal to negative 1 over L times T. And it really doesn't matter exactly how you write it. It'll work out in the end. And we're going to integrate this. And this time we have to be careful because we're not integrating from 0 to I max. That's going to give us issues. We're actually integrating from I max to I because we already have current when we first open the switch. And if we put in 0 for our lower bound on this integral, we would have some major issues with the math. So this will go, that's a dt, and that's a di. Okay? So then when we plug this in, we're just going to get, basically, I'll write over here, 1 over r times the natural log of I prime, evaluated from I max to I, is just going to be equal to negative t over L. So we bring the r over to the other side, and we take the exponential after we evaluate. So that would actually be natural log of I over I max. So we take e to that, and we're going to get I over I max is equal to e to the minus t times r over L. And remember we said that tau RL is actually equal to L over R. So this time constant can be put in here. So I is equal to I max times e to the minus t over tau RL. And so this is our equation for when we open the switch. And checking this with our thoughts on what should happen, we know that we start at some value I max, And rather than this dropping immediately to 0, it's going to decay exponentially. Now this exponential decay occurs exactly the same way as what we discussed with RC circuits. And that's related by the inductive time constant. So this is L over R, and it's the point when the circuit reaches 63% of its final circuit when you close the switch. So that was this graph. So after 1 tau, we're at 0.63 of the total. And it's also when we have lost all but 37% of the initial current. So again, if we have I versus time, and we start with I max and we come down like this, after 1 tau, we're at 0.37, which is I over E, by the way. Okay? All right, so that's kind of the basics of RL circuits. And in the next lesson, we're going to look a little bit more at the behavior of RL circuits. We'll do some practice problems, and then we'll talk about energy stored in an inductor. But one thing that you might be wondering is, how is it possible that L over R is actually equal to 1 over seconds, or seconds rather, because we have e to the minus t over tau, and so tau has to be in units of seconds. So how is that actually possible? Well, let's try this real quick, and L over R is going to be henries over ohms. Okay, now let's think about this. We know that E is negative L di dt, so this means that L, or henries, is actually better expressed as volts times seconds divided by current, amps. So that means that the henry is a volt times a second divided by an amp. But we have to take that and we have to divide that by ohms. But remember from Ohm's law, V equals IR, so that means R is V over I, which is volts per amp. So that goes away and that goes away, and that's a really nifty quick proof that tau RL, L over R in other words, really does have units of seconds. Okay, so next time we'll talk a little bit more about the RL circuit, and we'll talk about energy stored in the magnetic field of an inductor.